Time for us here to take a look at Lightwave's expressions. Now, this is an area of Lightwave that a good many people sort of shy away from. It's perceived as difficult or unintuitive or whatnot, but really it's actually not that bad. It's reasonably simple. The main difficulty in expressions just comes from when you get into more complex expressions. They can get quite long, and making sure that you've got all of the right spelling, the right kind of notation can be a bit of a pain, but beyond that it's actually quite straightforward. What expressions allow you to do are basically the same sorts of things that we've seen many times with all of the other constraints and motion controls. They just let you create relationships between an attribute in one item and apply that to an attribute on another item. When I say attributes, I mean channel attributes, so those would be things that can appear in the graph editor. Generally, of course, we see that this is stuff like position, rotation, scale, but also, of course, you've got attributes in objects like their morph channels. You've got attributes in constraints like the position item blend amount, stuff like that. These are all channels that can be accessed through the graph editor. Therefore, these are all things that can have expressions applied to them. Put simply, any animation channel that is available in Lightwave can be driven using an expression. So the first thing to get used to with expressions is the syntax. It's how you actually type stuff out, how you reference the attribute that you're trying to create a relationship toward. Now, there are two types of syntax available to be used in Lightwave expressions. There is what you would call bracket notation, which is somewhat similar to how you would write out algebraic expressions. And then there is L-script notation, which is more how you would write things out in, well, L-script, or a programming language. Bracket notation, as I say, very similar to algebraic notation. Let's imagine we have some sort of an expression which is 3 plus 4 times 7. Now, ordinarily when you do stuff like this, you multiply and divide, then you add and subtract, so brackets aren't needed. But let's just ignore that for a little minute and think about the two ways in which this could be interpreted. It could either be interpreted as 3 plus 4, which is 7, and then that result multiplied by 7, right? Or we could interpret it as 3 added on to 4 lots of 7. We use brackets to separate out parts of things. And this is basically how we write things in Lightwave expression bracket notation. The first thing you want to do, of course, is to get the name of something, the actual channel that you're trying to pull a reference from. Names of channels are always given in square brackets like this, and it goes the name of the item dot, what I'm going to call here type dot chan, which would be the channel, and then another square bracket to enclose it. So, for instance, this might be something along the lines of my null dot position dot z. That would be the z position of an item named my null. Notice the capitalization is important. In the case of my null, that would have to, of course, be what I had named the null. If when I'd created the null it had been done as my null like this, then using capitals in the expression wouldn't work. That has to match. But the capitalization at the beginning of position and of course the capitalization of the z are important. So perhaps I'm taking the z position from my null and I'll do plus 3, and I would apply this to some channel, and so whichever channel I applied it to would get the z position of the my null object plus 3, which would of course be in meters. So there is that. There's a wonderful little opportunity here to show something off that always catches people, and that's what you do when you are subtracting. Notice what I've got here. I've got minus space 3. This is important because of course with the space this says subtract 3 from this value. Without the space, then this is the value -3. This wouldn't work. This would. Because my null dot position -3, what does that even mean? Well, maybe it could be multiplied by -3. But if you wanted to subtract 3, then you must have the space. And similarly, putting a space like this would make no sense either. Multiplied, subtract 3, because it reads some value multiplied by subtract 3. Makes no sense. So let's take a little look at this here. I've got the camera selected, currently in Graph Editor, and you can see how easy it is to find the names of something, because you see here it is camera.rotation.h. So when you're looking up names for things, you can just get them directly from the channel list. So I'll create a new expression here. You'll notice by default it enters this value. We'll talk about that in a few moments. But for now, what I'm going to do is I'm just going to put a square bracket and type light.rotation.p. So this gets the pitch rotation of the light. And with the heading channel of the camera there selected, I'm going to click apply. And what we see we now have is a link whereby the camera's heading value follows the light's pitch value. Simple as that. I could multiply this by 3, and we see that now the camera is turning 3 times the pitch value of the light. It really is that simple. But I can start to pull in other channels as well. 3 in this case is a number, but of course light.rotation.pitch is also a number. It's a reference to a channel, the pitch channel, and that channel on the light has a value. That value is a number. So what I could do as well is I could perhaps say light.rotation.p minus light.rotation.b for the bank. So now I am getting on the camera 100% of the light's pitch value there, but it will subtract off an amount equal to the bank value. At the minute I'm going into negative here on the bank, so I'm subtracting a negative number, which is the same as adding the positive one. And of course if I go into the positive there, we see that we're turning back again. So what have I got here? If I get them both to the, or at least close to the same, 25 point some odd, you can see that of course the camera is now rotated to pretty much 0 on its heading. And that really is all that there is to writing expressions. Obviously, of course, the number and myriad of expressions that can be written and how long they can go on for can be massive. Hardly something we can cover here. But this gives us the basic idea of it. Now we saw before when I did that first little number example that I used round brackets or parentheses. And of course the expression syntax takes these as well. So that little 3 plus 4 times 7 thing would work perfectly well here. So let us say that I wanted to take the light's rotation pitch minus the light's rotation bank and multiply the result of this by, I don't know, 2. What I would do is wrap this in parentheses like that. This now makes what's inside those parentheses return down to a single value. I could then multiply that by 2. At the minute that's going to be 0, but as we can see if I start adjusting things here, we are indeed getting a value that is equivalent to the light's pitch minus its bank, and that whole thing multiplied by 2. Alternatively, of course, we could put the brackets in a different place. So instead of having that, maybe I want the light's rotation pitch minus the result of the bank times 2. So I would put the brackets there, and as we can see, different result. Can this be complicated? Sure it can, because maybe what I wanted to do was have this whole thing resolved to a single value as well, so I could put another set of brackets around it like this, and then perhaps I could subtract, I don't know, 50 from the overall result of that. So you see I've got bracket here, another bracket here, a double bracket over there. This is the only really difficult part about writing expressions, is that once you've got these brackets and these, you know, operators going all around all over the place, you can just sort of get a bit lost. You can forget or miss putting in a certain bracket. You might, you know, sort of miss the shift key and wind up with something like this, and you hit enter and the expression editor puts in these little arrows to show you that you've made a mess up somewhere. Basically, the arrows are put in there to show you that it cannot find a certain channel that you have created a reference to. Alternatively, if you were to miss out a bracket somewhere, like I missed that one, then you'll see that the thing is saying here uncompiled. it's grayed out, of course. That's basically replacing the apply button to tell me you can't apply this to anything because you've mistyped it. So it's very exacting in how things have to be done. Of course, it is a computer after all. It needs to be told specifically what to do. It can't figure it out for you. But the honest truth is, this is the only hard part about writing expressions. Spelling, essentially. That's the difficulty. Okay, so we've got something's name, dot, the type of channel, and the specific channel itself. That's great. That's the expression type notation. As I said, however, expressions can also take else script notation. Now, if you're new to expressions, you may not want to dive into this straight away. You can do pretty much everything with this normal notation anyway. But else script notation can have its place in certain places. If we were using else script notation, then it would look, to write exactly the same thing, would look like this. Name dot type, which I'm just going to miss the E off and use a small t. Seems a bit weird. Don't worry. Brackets, when, brackets, little c, which stands for channel. Okay, this seems weird, right? Let's take it apart a little bit and look at it in the case of the example of just, let's say, the myNull. So I've got myNull. Now, what's the type? Well, that's position, rotation, scale. So pos means position. Notice lowercase p. When? In else script notation, you have to specify the actual time at which you're grabbing the position from, the point in time where it comes from, when this value gets evaluated. Else script has a reserved word for this, which is time. The reserved word time means now, the current time now, wherever you happen to be in the timeline or in an animation, now. If you wanted 1 second before, it would be time minus 1. And then at the end, another dot and the channel. Let's say x. Notice again, lowercase. So myNull.pos brackets time x is absolutely identical to myNull.position.x. These two things are equivalent in the expression editor. Now, of course, we see the time variable that is always used in else script notation, but that is also available in bracket notation. So if, for instance, I were wanting to get the x position of myNull at a different time than the current time, so this would allow me to, of course, have the item that I'm using, delayed in time or running ahead in time, then I can do comma, space, time with a capital T, and, at whatever, let's say, minus 1. This would be absolutely equivalent to typing this here. So let's do this here. Let's have the light.rotation.p, comma, time, space, -1. What I need to do now is just create a short little animation, which is probably rubbish, but still, there we go. And what we see the camera doesn't move, it stays put for 1 second. That in this case is frame 24, because I'm at 24 frames a second in this scene. And then after that, it starts to turn. And you see it keeps turning for 1 second after the light has stopped. It's grabbing the value of the light's pitch channel at time minus 1 second, or at current time minus 1 second. So when I'm at, say, frame 80 here, the camera is getting what the pitch rotation was 1 second or 24 frames earlier. You don't have to use time. Usually it is best to use time, because of course that makes your expression frame rate independent. You can turn the frame rate up, you can turn it down, and the amount of trail in time will remain constant. You can, if you wish, use frame. I'm going to set this to -10 there, and what you now get is the camera lags 10 frames behind the light. Now, of course, what this would mean is if I were to shift my frame rate, then the amount of time delay going on would, of course, be different. That's why it's usually better to use time than frame, but the option is there should you want it. And of course, don't forget, I'm using minus here. You could just as easily use plus, because of course the computer is able to look ahead on the time channel of things, And we can see there that, of course, the camera stops rotating 10 frames before the light has stopped rotating. It is preempting the light's movement rather than trailing it. So whilst I could go on here and just show more and more and more examples of things in terms of, getting the right notation, it's kind of pointless because I say there's just a near infinite number of possibles that we could go through. Now, time represented something specific. It was what we would call a reserved word, and it represented time now, or time plus minus multiplied by whatever value we wanted. The other thing that we saw initially that I did say we would mention is, of course, the value. This again is a reserved word, and what it means is this channel's current keyframed value at time now. So you could have something along the lines of value plus light.rotation.p like this. And so that would give you the camera's keyframed value, which at present is 0, plus the light's pitch rotation value. This essentially lets you make an expression additive on top of keyframes that you already have on a channel. You do have to be careful using this though, because let's notice that at the minute, owing to the expression, my camera is going to 47 degrees, which is of course the value of the pitch channel on the light here. If I keyframe the camera, then of course it records 47 degrees as the current keyframe and adds on the result of the expression again. If you're going to use value to make some expression additive on top of keyframes, you can't really keyframe things directly in the viewport here. You would either have to come to the graph editor and enter the values directly, or just type the values in to the window here. So if I just type 30, then you'll notice that that 30 becomes 77, which is 30 plus the 47 from the light. But if I just go round keying here, it just jumps quite a lot. So let's just have a look at some of the additional features that we've got here. First off, if you notice the expressions tab here, which will list all the expressions that exist in your scene, you can toggle them on and off so as they are active or inactive. Of course, you can see that a channel has an expression applied to it because it gets this little spot next to it. If you pull up an expression from the expression list, you can hit Get Channels, and that will get into the channel bin whichever channels in the scene have that expression applied to them. Of course, you can have multiple channels on different objects all using the same expression. You then have this fella, the builder. If you are new to making expressions or writing expressions, this is by far the way to go, because what it does is it gives you some kind of presets that you can use to start building your own expressions. Let's have a look at something like this, clamped map range. This is where you start to go beyond just the normal syntax and notation of things, and you actually get into some of the functions that are in expressions, which is some of the other great stuff that we've got to do. So let's have a look, right? I've got this guy here, and we're going to look at functions for him. So let's say we use the clamp function. What clamp does is clamp the output of an expression between certain values. So if I type clamp, and then of course it is a function, so the references for the functions go in brackets. This is the input value that I'm clamping, the light's pitch at frame plus 10. I then put a comma followed by the minimum clamp value, so let's say 30 space comma maximum clamp value, let's say 60, and another bracket. In this case, these parentheses, these rounded brackets, are defining what's inside the clamp function. So let's enter that, and what do we see? Well, we see that the camera is indeed following the light just as it was doing before, but its range is now clamped. It will only go between 30 and 60 degrees. In a very real way, this is just like the motion limits that we have on the motion options panel. You will have seen, of course, when we were looking at motion limiting way back at the beginning, that the motion limits would not clamp and limit the result coming from expressions. This is how you would clamp and limit the results coming from expressions. So how's about that old map range then? Well, let's just have a little peek. I'm just going to get rid of that frame thing there, and of course the clamp function, that can go away. Okay, so what map range allows us to do is to take input values coming from something and remap those to another set of values. So for instance, at the minute here, we're just getting the light.rotation.p, right? It's a one-to-one match. We saw, of course, that we can add a value to it, subtract a value from it, we can multiply it by something. Map range is a bit like that, but a bit more clever. So if I do map range, and then bracket to enclose whatever is in the map range function here. I've put a space there, that's not important, I'm just doing it for clarity. So map range, the light's pitch rotation. Now, you then take the input min and the input max, so comma, let's say 10, comma, 100. This means that I'm grabbing the light's pitch rotation between the values of 10 and 100, and I'm going to remap those to, let's say, 30, comma, 60, and of course close brackets. What this means is that when the light is at 10, the expression turns that into 30. When it receives the input 10, it remaps that to output 30. When it receives 100, it remaps that to output 60. And of course, intermediate values between 10 and 100, as well as extended values below 10 or above 100, will fit the same mapping. So what we see is that when my light is at 0 on pitch, the camera is not at 0 on heading. It's mapped differently. To get the camera to 0 on heading, I have to come to negative 70 some odd, negative 80-ish on the light there. Similarly, as the light comes round to 100 degrees, the camera is now at 60, and as it comes round to, let's say, 200 degrees, we see that the camera has gone up to 90 odd. It's not the case that this is multiplication. It's not the case that at 100 it is 60, so at 200 this would be 120. It is a mapping between ranges of value. And what we can do with functions is to bracket them up in the same way we did with values, to compact them like single numbers to operate on. So if I've got a map range here, I can do a clamp, bracket, and now I'm clamping my map range function to between, let's say, 10 and 90. So now the camera will follow the light as per this map range amount, but it won't go below 10 degrees and it won't go above 90 degrees. So not only can you work with expressions based on simple numbers, multiplying things up, subtracting values off, whatever else, you can also use functions to be able to limit values, to remap ranges of values, and a whole range of other things that, of course, we see here in the builder. We also see that we have conditional functions, equal to, greater than, less than or equal to, and so on. So we could have something like this, where we say if the light's pitch rotation is strictly greater than the light's bank rotation, then the expression will output 20, else it will output 60. So let's just attach that there to our camera's rotation channel, and we see that it just comes out at a fixed amount there. You'll notice that turning the light on pitch is having absolutely no effect until the point where the pitch becomes less than the bank value, and now you see the camera jump back to 20 degrees. So not only can you create a simple link between one thing and another, just like a constraint, of course allowing you to add constraints to channels where you normally can't add constraints via motion options like morph channels or texture channels or anything else. You can also put those constraints onto something of a sliding scale with functions like map range, and you can also make it so that those constraints will only apply, will only kick in if a certain condition somewhere in the scene is met. Huge range of possibilities here in using expressions like this. So as I say, so many possibilities that can be brought out. You could probably do a whole range of tutorials just on this sort of, method and practice alone. One little side note I want to make on the topic of numbers whilst we're here is the number 1 in expressions. Obviously, we have different kinds of channels. We have position channels, rotation channels. We also have percentile channels. In the case of a morph, that goes between 0 and 100%, or negative 100%, or 200%, whatever. Or, of course, in blend values for IKFK blending or constraint blending and so on. Those are also percentile channels. The number 1 in expressions means slightly different things in different contexts. In the case of a position channel, it means 1 meter. In the case of a rotational channel, it means 1 degree. And in the case of a percentile channel, it means 100%. So if you're writing an expression for a percentile channel and you're trying to manipulate the value up to 100%, you don't use the value 100, you use the value 1. Or 2 if you're going to 200%, and so on and so forth. So, with that noted then, continuing on. One additional thing that I do want to point out, of course, is that we had the motion modifier for expressions here. This gives us a couple of extra little things. First of all, the expression can be additive on whatever the item's keyframes already are. That's kind of like using the reserved word value in a way. But of course, the motion expression via modifier can also be set to work after IK. There is, however, a caveat to this, and that is that expressions will only work after IK if they are using L script notation. It's something that gets a lot of people. They have an expression that they've done, they want it to activate after IK rather than before, they put it in here and the after IK switch appears not to work. That's the reason why you must use L script notation. So there we go. Those are Lightwave's expressions in a nutshell. As you can see, of course, there's a great myriad of things that you could potentially do with them. And I'm sure you could probably do a many-hour-long tutorial series on expressions alone and showing all of the various clever little tricks that you could pull off from using them. Hopefully this introduction is good enough to get you started on the basics, and certainly if you are newer to expressions, the best place to go is the builder. There's so many bits of information, examples, applications that can be used for different types of functions and things here, and that will really help you learn and get started, and of course enable you to write expressions just by picking things off drop downs like this, which will of course get all of the notation, bracketing, capitalization and so on right for you, which will help you avoid those kinds of little mistakes there.